All right, let's dive into a really fascinating mathematical puzzle today. It's a real head-scratcher that seems to just break a fundamental rule of algebra. This is one of those cases where what you absolutely expect to happen, well, it just doesn't.
I mean, it seems totally logical, right? You've got a function and its inverse function sitting right next to each other. One should just undo the other, leaving you with plain old x. It's like one of the first things we learn about inverse functions. But what happens when you actually put it to the test?
Yeah, this is what you get. We expect arcsine of 5 pi over 4 to be, well, 5 pi over 4. Simple. But if you punch that into your calculator, it spits out negative pi over 4. Whoa! That is not even in the same ballpark. So what on earth is going on here? To solve this little mystery, we need to go and check the official rulebook.
Okay, so to figure out why our functions are misbehaving like this, we've got to go back to the fundamental laws that govern all inverse functions. And there's one rule in particular that is the absolute key to cracking this whole case. And that rule is called the horizontal line test. You can think of this test as the gatekeeper for inverses. If a function can't pass this test, then technically it can't have a true, well-behaved inverse function. So, what is this test?
It's actually beautiful in its simplicity. Here's the deal. If you can draw a single horizontal line anywhere on a graph and it hits the function more than once, it fails. That's it. It's a very strict one strike and you're out kind of policy.
And this brings us right to the scene of the crime. Let's take a closer look at our main suspect here, the sine function. Why is it causing so much trouble for its inverse?
The problem in a nutshell is that trig functions like sine are periodic. You know, they just repeat the same pattern of values over and over and over again, literally forever. And this creates a huge issue for our horizontal line test.
And just look at this. The sine wave doesn't just fail the test, it fails spectacularly. A single horizontal line can hit it an infinite number of times. This creates a totally impossible situation for an inverse. Think about it. If we ask, hey, what angle gives us a sine of 0.5? There are literally endless possible answers. This is the heart of our problem. And this is where mathematicians got really clever.
So, faced with this problem of infinite answers, mathematicians didn't just throw up their hands and give up. Nope, they came up with this really elegant solution, a sort of gentleman's agreement to make these functions finally play by the rules.
The idea was so simple, but so brilliant. If the whole repeating graph is the problem, what if we just agreed to only look at one tiny piece of it? You know, a piece that's actually well-behaved and follows the rules.
And here's that solution in action. This technique is called restricting the domain. We basically perform surgery, isolating just one little piece of the sine wave, this bolded section right here. Now, this section has every possible output value from -1 to 1, but it only has them once. And now, if you draw a horizontal line, it only ever crosses one time. This little piece passes the test perfectly.
So this is the really crucial point, this official agreement. For the sine function, the entire world of mathematics has just agreed that we're only going to look at the inputs, the x values, that fall between negative pi over 2 and positive pi over 2. This is now the official, well-behaved version of sine that we use to create its inverse.
So by agreeing on this one restriction, we've created a function that's officially invertible. Awesome. The next step is to actually find that inverse. And in math, the way we find an inverse, graphically, is by reflecting the function across the line y equals x. Okay, so with this restriction locked in, we can finally define our inverse functions. So, let's meet the arcs family. Graphically, creating an inverse is kind of like holding a mirror up to our function along that diagonal line y equals x. So when we reflect that small, restricted piece of the sine wave, we get a brand new function, arc sine of x. And this new function, it has its own set of rules, which are directly inherited from its parent.
And listen up, because this is the absolute most important key to our entire puzzle. The restriction we put on the sine function's input doesn't just vanish. It gets passed down to the inverse function as a strict rule for its output. What this means is that the arcsine function is physically incapable of giving you an answer outside of that negative pi over 2 to pi over 2 range. It's hard-coded. This slide right here is our cheat sheet. For every single inverse trig function, its set of possible answers, what we call its range, is strictly defined. Arcsine can only ever give you an answer between negative pi over 2 and pi over 2. Arc cos is locked between 0 and pi, and so on. This table is literally the key to solving our puzzle.
Okay, we've gathered the evidence, we understand the rules. Now, armed with all this new knowledge, let's go back to the original problem and crack this case once and for all.
Here it is again, arcsine of 5 pi over 4. Only this time, we're not going to be surprised by the answer. Nope. This time, we're going to use logic and follow the rules we just learned.
Let's walk through it together. Step 1. We evaluate the inside function. The sine of 5 pi over 4 is negative root 2 over 2. Easy enough. Step 2. This reframes our whole question. We're now just looking for the arcsine of that value. Step 3, and this is the big one, we check the rulebook. Remember, the output of arcsine must be between negative pi over 2 and pi over 2. So, for our final step, we have to find the angle inside that very specific range that has a sine of negative root 2 over 2. And in that little window, there is only one possible answer, negative pi over 4.
And that's it. That's the solution to the mystery. The functions don't just blindly cancel each other out. The outer function, the arcsine, it acts like a filter. It takes the result from the inside and then finds the equivalent angle that actually fits within its own strict predefined output range.
And just to really see it, if you look at the unit circle, it all clicks. The angle we started with, 5 pi over 4, and the answer our calculator gave us, negative pi over 4, they actually point to the exact same spot on the circle. They're called coterminal angles. So see, arcsine didn't actually change the direction, it just found the official name for that angle that was allowed within its rulebook.
So, it turns out the rule breaking was actually a rule itself, a new, clever rule that we invented to make an impossible situation possible. It really makes you wonder, doesn't it? How many of the rules in math aren't really rigid laws we discovered, but are actually just elegant agreements we all made up to solve tricky problems? What other rules are just clever workarounds we've all agreed to follow?